Hi, welcome back to the channel and video number 112. As the title suggests, this video will be discussing the technical aspects of Raptor NG, which is a follow-on to the original Raptor with the Audi V6 diesel engine. I discussed a lot of the problems with that design in a video a couple months ago, and unfortunately that original Raptor ended up in a cornfield in Nebraska on August 6th after having cooling issues and then a redrive failure. Kind of as I predicted. I discussed some of those possibilities in that video. Anyway, this one's going to discuss the next generation. We don't know much about it so far, but we do know it'll be a ducted fan hybrid electric design. And I'll just go over some of the technical challenges that sort of configuration might face. So here's the preliminary render of the Raptor NG. Very nice looking design. However, I don't know how functional it's going to be. First of all, the fans placed over top of the wings like this, very unusual. Probably not a very good idea from an airflow point of view over the wing. The fans, depending on how much air they're moving, could really affect the airflow over the wings here. Throttling back could maybe cause the air to actually back up in front here or try to find its way around. Probably should be on pylons, maybe mounted off the side of the fuselage, but like this, I don't think it's a very good idea. Second thing is this new box wing configuration. Very low aspect ratio. That usually means high induced drag at low speeds or even medium speeds. The span of the main wings here is only about the same as the canard. Probably not a very good idea either if you're looking for range and efficiency at high altitude. And thirdly, the very short span here and the configuration probably will mean some sort of roll instability as well, in my opinion. I'm certainly no aerodynamicist, however, this short span design here, low aspect ratio, doesn't look like a good way to go. So the stated plan for Raptor NG is to use a hybrid electric layout, and that's similar to a Toyota Prius, which uses a piston or internal combustion engine to drive a generator that can charge the battery or feed power through to the controller and then to the electric motor. Also in the Raptor, it would be possible to use a turbo-driven generator that would be able to extract a little more energy from the fuel. You can feed that power to the battery or directly to the controller and then to the electric motor. So normally with a piston engine driving the propeller directly, 100% of the power from the engine would go into driving the propeller. However, with the hybrid layout, we have some losses along the way. The generator is only maybe about 95% efficient. Battery, depending on how much current you're drawing, the type of battery might be mid-90s to high 90s. You can feed the power directly to the inverter. The inverters are pretty efficient, about 98%. And then some good electric motors, also around 95%. However, when you add all these together here, the total loss is around 12%. So you only get about 88% overall efficiency compared to 100% with the piston engine driving the propeller directly. So that has to be taken into account. Really what that means for an airplane, which operates at high continuous power, you need an engine putting out about 12% more power than you really need compared to the electric motor. And we're just going to brush up a little bit on power here. So sometimes we're talking kilowatts or watts. 746 watts equals 1 horsepower. 1 kilowatt, which is 1,000 watts, equals 1.34 horsepower. And 1 kilowatt hour equals 1,000 watts for 1 hour. So these will be important when we look at some of the other charts here. So in the Raptor NG design, the electric motors will be driving this fan unit here. And typically the fans have usually 6 to 18 blades on them. Depends a lot on the design. And they also have some blades that are fixed behind here called stators. And these serve to straighten out the airflow and usually gain quite a bit more thrust. So you might wonder why you don't see too many ducted fan aircraft around in general aviation. Well, one of the reasons is that ducted fans perform rather poorly at high speeds. And you can see from this chart here, which is fan thrust versus speed, we have the thrust force here in pounds, speed in knots here. You'll see we might start out with 400 pounds of static force. In other words, with the aircraft not moving. However, by the time we get to 200 knots, this has fallen down to about 115 pounds or so. And that doesn't make for very good high-speed performance, obviously. So this chart just gives a general idea of what's in play here. Here we've got force or thrust. Here we have speed. And you can see the thrust here on the orange line drops off as the speed increases. And the drag, of course, goes up the square of the speed roughly. You can see where the thrust meets the drag. This is going to be the maximum speed of this aircraft here. And this was a model aircraft ducted fan. It's just representative. The same things apply to a full-scale airplane. And you need very high input horsepower with a ducted fan to achieve high speed in flight. And that's why they're just not a very good choice for a fast aircraft. So here's a ducted fan setup. This is the Russian PJ-2. This is kind of a replica fighter aircraft with twin 27-inch ducted fans driven by a single LS engine in the fuselage. You can see the drive shaft here, which comes out to drive the fan. And it's got a splitting gearbox, so crankshaft power is split off through gears, and two drive shafts, one on each side. And you can see the composite blades here and the stators as well. Here's a few photos of the Russian PJ-2. This was developed by a small group of enthusiasts on a rather small budget. Very interesting design, and it's one of the few ducted fans that's actually flown. They hope to offer this as a kit in the future. And here's a shot of the PJ-2's custom gearbox. Engine bolts up here. Got the gear train here. We've got two output shafts, one for each side to drive the fans. Here's a close-up of one of the composite fan blades from the PJ-2. You know, it's a pretty intricate piece here. Carbon fiber molded into a metallic shank here that's attached to the hub. Not a really easy piece to manufacture, I don't imagine. You've got to make a lot of them for a ducted fan. And here's another shot of the PJ-2 fan setup, this time from the front side. You notice the hub here where the drive shafts bolt up, fan blades here, stators here, and towards the blue part is aft. And the reason I'm showing you this is there aren't too many ducted fan airplanes. I just wanted to show general layouts of actual existing ones, not theoretical ones. And here's a side-by-side comparison of the original blade for the PJ-2. And this was just a 3D printed version of the new design that should put out hopefully something like 15 to 20% more thrust for the same input horsepower. You can see they've gone to a broader design and a slightly different shape. So there's a lot to know about fan design. It's quite a bit different than propellers. Some of it can be done theoretically, but there's nothing like building a set of blades and flight testing them to find out how good your compromise was from low speed static thrust for takeoff to cruise performance. So this is a great photo here of the PJ-2 showing the twin ducted fan layout. Each fan here develops about 440 pounds of thrust with an input horsepower of around 194 horsepower into each fan. And the second ducted fan aircraft we're going to look at is the UL-39, developed by the Czech Technical University in Prague. This used a single 23-inch ducted fan that was designed by them, driven by a BMW 1000cc bike engine through a gearbox. And this fan developed about 393 pounds of static thrust at about 150 horsepower. Fan efficiency at 155 knots was about 66%. And this aircraft was lost in an accident, recovered, but they've decided to build a Mark II version, slightly different. It'll use a Bombardier jet ski motor supercharged, and that will drive a revised fan, and they're hoping it'll be somewhat more efficient than this was. And I might add that the Czech Technical University had full wind tunnel capability, high-end CFD to develop this aircraft, as well as the fan system. And it was a work over many years. Many graduate engineers worked on this project. Very interesting, and I think they did a really good job. Of course, you learn a lot building stuff, and Mark II hopefully will be even more successful than this was. They're looking at some military training versions of this, and I hope this project works out. And the last ducted fan aircraft we'll look at here for comparison purposes is the Airbus E-fan. This was developed a few years ago as a technology demonstrator, and this is purely electric. It has a battery pack driving twin ducted fans. There's no internal combustion engine, and this one eventually flew across the English Channel. Pretty successful for a technology demonstrator. However, as far as comparing to an equivalent propeller-driven airplane, performance of this aircraft falls quite a bit short. It's a consequence of the ducted fans. They don't work very well at high speed. And the airplane was designed around kind of low horsepower requirements because it is essentially just battery powered. You can't have high induced drag, so they have pretty high aspect ratio wings, quite a bit of wing area, and that impacts the performance. But overall, for its intended purpose, pretty successful. And of course, Airbus has a lot of talented people. They have very best CFD and a lot of money to put into something like this. And here's a close-up photo of the fan layout on the E-fan. You can notice the fan blades here and the stators here. And I believe this also had variable pitch fan blades, which is very interesting. So that might have allowed them to get a better compromise between static thrust or takeoff thrust and high-speed cruise. As far as thrust developed, static thrust, it was fairly impressive. These are about 30 kilowatt motors, so about 40 horsepower, and each one developed about 266 pounds of thrust static. So that's quite good. Speed-wise on the top end, though, it didn't perform very well considering. So with about 80 horsepower combined between the two electric motors, the airplane achieved a maximum speed of about 120 knots. Nothing to write home about. If you compared that to, say, some 80 horsepower Rotax powered aircraft, sport aircraft out there, they're quite a bit faster than this. However, this was a technology demonstrator, as I said. Speed wasn't its primary goal here. It was just to show what could be done with ducted fans driven by electric motors and lithium batteries. So you can see the whole E-fan design here. And of course, the ducts themselves present extra drag, and that drag goes up exponentially with speed. And you've got some extra weight as well. Some people say the duct increases the static thrust. That may be true, however, in the case of ducted fans with small diameters like this, they can't develop anywhere near the static thrust that an open propeller does. So you've got less thrust, more drag, and those two things conspire against you for a high-performance airplane. So Raptor NG will need a very large generator. And just to give you some idea of the size, this is the variable frequency starter generator off a GEnx turbofan engine. And it has two of these. These put out 250 kilowatts each. And you can see the relative size from the mechanic's hand here. It's a big piece of kit. And these weigh about 200 pounds each. So this would be about the minimum size Raptor NG could use. And I don't know what else is out there for generators, but probably going to weigh at least 200 pounds like this unit here. So I talked about a turbo generator earlier in the first part of the video. And what is that? Well, the new generation Formula One cars use these. They're using exhaust gases to drive a conventional turbocharger centrifugal compressor, and the shaft is also going forward here to drive a high-speed generator. So the air is coming in here, being compressed by the compressor. Compressor discharge air is here. Exhaust in here, exhaust out here, and electrical power generated and carried out through these cables here. So I don't know if Raptor NG will incorporate one of these, but it would be a way to get a little more energy out of the fuel. The main engine would be, of course, turning a generator as well, and this could add, like I said in the original graphic there, another 15 or 20% power could be used to charge the battery or drive the electric motor, driving the ducted fans directly. So what do we have for electric motors out there to potentially power Raptor? Well, we've got some very high-tech, likely rather expensive developments by partnership between Denso and Honeywell. This is a dual motor setup driving through a combining gearbox to drive a single propeller or ducted fan perhaps. And power on these is generally provided by a turboshaft-driven generator. Of course, Honeywell builds turbofan and turbojet APU engines. That's their specialty. Denso has a lot of experience building electric motors, hence the partnership. This particular one probably isn't well suited to drive fans on the Raptor, but it just shows kind of what's under development for electric or electric hybrid airplanes in the future, perhaps. So couldn't we just use a couple of Tesla Model S motors? Yeah, they weigh about 70 pounds, somewhere around 360 horsepower. However, the big problem with a lot of the automotive ones are they won't put out this sort of horsepower continuously due to the slight inefficiencies on them. You do have to cool them, and in an airplane you need that high continuous power. So most of the automotive-based ones are probably not suitable. You need something that's rated at something like 200 to 300 kilowatts, and that's a lot to demand out of an electric motor. It needs to be rated for 100% duty cycle in an airplane, so that aspect is quite different than cars. And these are some new technology motors out of Magnax in Belgium. They are axial flux permanent magnet motor, and they've got a 250 model, a 250 millimeter, that's about 10 inches in diameter. It's rated at 230 kilowatts peak and about 120 kilowatts continuous. This is their 275 model here, and I believe it's around 300 kilowatts peak and about 200 continuous. 250 weighs about 60 pounds, which is pretty good, and I imagine the larger 275 is probably around 70 or so, 75 perhaps. And here's what the Magnax motors look like inside. You can see they're a little different construction than the typical radial type permanent magnet motors. They do have provisions for cooling as well. Obviously these can generate a lot of heat, and they're a pretty small package. Anyway, these are somewhat lighter than the older radial type motors. They conserve copper and magnetic materials as well due to the design of them here. And here's an illustration of the radial flux design here versus the axial flux design. So what engines could be used to drive the main generator on the Raptor NG? Well, the LS V8 engines are available in crate form, 400 to 500 horsepower, fairly light, fairly inexpensive, very reliable. You could perhaps save 100 pounds by going to something like the Mercedes M139S engine, also around 400 horsepower, but not so available. So finally, I've done a comparison of a direct drive propeller system versus the hybrid electric ducted fan system. And I've used a Lycoming turbocharged 540 here. This would be driving a conventional propeller. And here using the LS3 engine, V8 engine, and the Mercedes 139S turbo engine, 4-cylinder, as we've discussed before. So we're just looking at horsepower here. Lycoming puts out 350, the LS 430, the Mercedes 416. Dry weight, well, both the automotive engines are lighter than the Lycoming. However, as we add up all the other components needed for the hybrid electric system, we'll see that the Lycoming ends up considerably lighter here. So obviously the Lycoming doesn't need generators or inverters or electric motors or the cabling or the turbo generator or the electrical cooling system. But in the end, the Lycoming package weight comes out to 642 pounds. The LS, with all the other pieces added here, and the battery, 50 kilowatt hour battery, which only lasts about 10 minutes at rated power. Just enough to get the airplane down safely. That's the big killer here, is the battery weight. And with everything combined here, the LS package weighs almost 1,000 pounds more than the Lycoming would. Mercedes ends up to be about 100 pounds lighter, just because the engine is about 100 pounds lighter. It still needs all the other things that the LS would need here. So as far as I'm concerned, this is a big deal breaker. There's no way that an effective hybrid electric system with ducted fans is going to end up lighter than the Lycoming 540. And also, as we've seen, the ducted fans probably won't provide anywhere near the thrust performance at high speed that the conventional propeller will and the direct drive engine. So while the Audi engine was very heavy in the Raptor 1, the Raptor NG setup is going to be even heavier than that. And this graphic just shows my prediction of Raptor NG's performance if they get the fans to work really well. And I think it will actually be worse than this. Just comparing it to an RV10, both at 17,000 feet, both at 175 knots. This would be the fuel burn of the RV10, which is about 10.5 gallons an hour running lean of peak. And with the Raptor here, we're at about almost triple that, about 30 gallons per hour. And that's a consequence of the losses in the hybrid system, as well as the inefficiency of the ducted fans and the airframe design of the Raptor at high speed. A lightweight hybrid electric system will probably require a turboshaft-driven generator like this one from Honeywell. Yes, they're expensive. Yes, they burn a lot of fuel, but they are reliable and they are light. You have to question the hybrid electric idea at all, though, in general aviation aircraft. Makes much more sense just to use either a turbine engine or a piston engine to drive a propeller, as Raptor 1 had originally. It's far more efficient than this setup will ever be. And one more thing we need to consider, of course, is the cooling of all these components. The battery, the inverter, the electric motors, etc., as well as the piston engine. Heat has to be dissipated here. That means more drag and more power required to overcome that drag. With ducted fan efficiency likely being well under 50% above 200 knots versus 80 to 85% with a traditional propeller. Doesn't look like this will be meeting the mission for high speed. Also carrying all that extra weight just means longer takeoff distance, lower rate of climb, higher fuel burn, less range, high noise. This is just a bad choice, and you just can't defy the laws of physics here. Time will tell, of course. We'll have to see how this all shakes out as Raptor NG progresses.